Picture yourself standing on the highest peak of a mountain, the wind whipping past your face as you look out over a sea of jagged rocks and sweeping ridges. Now imagine this: every stone beneath your feet, every cliff face rising around you, was once at the bottom of an ancient ocean. This isn't some far-fetched fantasy or science fiction plot. It's the breathtaking reality of our living, breathing planet. Deep within the very bones of Earth's most majestic mountain ranges lie the ghosts of vanished seas, hidden in plain sight, waiting to tell their story. Today, we're embarking on an extraordinary journey to unravel one of geology's most captivating mysteries: the incredible phenomenon of long-buried ocean floors resurfacing as towering mountain chains. From the snow-capped peaks of the Himalayas to the volcanic ridges of the Andes, these geological transformations represent nature's most spectacular recycling program, a process that unfolds over billions of years, yet leaves its mark in every stone and stratum. This isn't just about rocks moving around, it's about Earth's memory, preserved in mineral form, telling us secrets about where we've been and hinting at where we're going. Throughout this exploration, we'll uncover the powerful forces that drive this incredible transformation, visit stunning examples from across the globe, and piece together what these processes reveal about our planet's evolution. We're about to dive deep into the story written in stone, a narrative of collision, pressure, and resurrection that will forever change how you see the mountains around you. So join me as we journey through time and rock, decoding the magnificent mystery of how ocean floors become mountain peaks, and discover why this ancient process matters more than you might ever have imagined. So what exactly is this ancient ocean floor we keep talking about? It's not just sand and mud, it's a complex geological structure with a very specific identity. Picture the deepest parts of our oceans, where volcanic activity constantly creates new crust along massive underwater mountain ranges called mid-ocean ridges. Here, molten rock from Earth's mantle erupts onto the seafloor, cooling rapidly to form basalt, a dark, dense rock rich in iron and magnesium. Deeper beneath this surface layer, the same magma cools more slowly, creating coarse-grained gabbro. Together, these two rock types form the backbone of oceanic crust, fundamentally different from the lighter, granite-based continental crust we stand on. This distinction is crucial because density dictates destiny in plate tectonics. Oceanic crust is heavier, which is why it eventually sinks beneath continental plates in the process that creates mountains. But before that happens, this ocean floor accumulates a detailed record of Earth's history. As millions of years pass, fine particles settle through the water column, microscopic shells of single-celled organisms, clay minerals from distant continents, volcanic ash from eruptions, and even metallic nodules that precipitate from seawater. These layers build up gradually, preserving fossils and chemical signatures that tell us about ancient ocean temperatures, chemistry, and even the atmosphere above them at the time they were deposited. Geologists can read these rocks like books. The basalt preserves magnetic signatures that record Earth's changing magnetic field, allowing us to determine not only when the rock formed, but also where it was located geographically at that time. The sedimentary layers contain microfossils that date the rocks and reveal what the marine environment was like from water depth to temperature and nutrient availability. Even the chemical composition of these rocks holds clues, with certain elements and isotopes indicating whether the material came from volcanic activity, continental erosion, or even hydrothermal vents on the seafloor. This entire package, the basaltic foundation, the gabbroic underpinnings, and the accumulated sedimentary layers, becomes the raw material that will eventually be transformed into mountains. When we find these materials in high mountain ranges, they carry their oceanic identity with them, allowing scientists to recognize their origin despite the incredible journey they've undergone. Understanding this starting point is essential because it helps us appreciate the profound transformation these rocks undergo, from forming at mid-ocean ridges to being buried deep beneath continents before finally being uplifted to become the highest points on our planet. But what provides the incredible force needed to lift an entire ocean floor thousands of meters into the sky? The answer lies in one of science's most revolutionary theories, plate tectonics. Think of Earth not as a solid, static ball, but as a dynamic system with a fragmented outer shell. This shell, known as the lithosphere, is broken into massive, rigid pieces that fit together like a rocky jigsaw puzzle floating on a hotter, semi-fluid layer beneath called the asthenosphere. These tectonic plates are in constant, albeit extremely slow, motion, moving at about the same speed your fingernails grow. This movement is driven by powerful forces deep within our planet. Enormous convection currents in the mantle act like a colossal conveyor belt, with hot material rising from near the core, spreading laterally as it cools, and then sinking back down again. At mid-ocean ridges, where new oceanic crust is born from upwelling magma, the simple act of pushing this new material outward creates what geologists call a ridge push. Meanwhile, at the opposite end of a plate's journey, when a dense oceanic plate begins to sink into the mantle at a subduction zone, its weight creates a powerful downward pull known as slab pull, arguably the strongest driving force in plate tectonics. The real magic happens where these massive plates interact, particularly when an oceanic plate meets a continental plate. Because oceanic crust is denser, having been formed from mantle material at mid-ocean ridges, it naturally sinks beneath the lighter, buoyant continental crust. This process, called subduction, marks the beginning of the ocean floor's transformation. But here's the fascinating part: subduction doesn't simply destroy the ocean floor. Instead, as the plate descends, pieces of it are often scraped off like butter on a knife, accumulating and deforming at the edge of the overriding continent. This relentless geological machinery has been operating for billions of years, continuously recycling Earth's surface materials. The same forces that create new ocean floor at mid-ocean ridges are responsible for consuming it at subduction zones, creating a beautiful planetary recycling system. This endless cycle of creation and destruction sets the stage for the most dramatic geological show on Earth, the birth of mountain ranges. Without this dynamic system of moving plates, our planet would be a flat, geologically dead world, devoid of the majestic landscapes that define our horizons and shape our climates. Now we arrive at the very collision point itself, the dramatic interface where this geological destiny is forged, the subduction zone. Picture this as the ultimate battleground between oceanic and continental crust, where the dense oceanic plate concedes and begins its long descent back into the mantle from whence it came. This isn't a gentle process, it's a violent, chaotic, and immensely powerful encounter that literally bends the very fabric of our planet, creating some of the most extreme landscapes on Earth. The most visible signature of this collision is the formation of deep ocean trenches, the absolute deepest parts of our oceans. These are not subtle features. The Mariana Trench, for instance, is so profound that if you placed Mount Everest at its bottom, the peak would still be over a mile beneath the ocean surface. These trenches mark the precise point where the oceanic plate begins to curve downward, a hinge line of incredible geological forces, but the action doesn't stop at the surface. As the plate sinks deeper, reaching depths of dozens of miles, it undergoes a remarkable change. The oceanic crust, which spent millions of years hydrating on the seafloor, is now subjected to immense heat and pressure. This forces the water out of the minerals, much like squeezing a wet sponge. This liberated water doesn't just disappear, it rises upward into the overlying wedge of hot mantle rock. Here's where something magical happens. Water dramatically lowers the melting point of these mantle rocks. Solid rock that would normally require unimaginable temperatures to melt now becomes a slushy, molten mass, generating vast quantities of magma. This newly formed magma, being less dense than the surrounding solid rock, begins a relentless upward migration. It eventually punches through the overlying continental crust, fueling the fiery volcanic arcs that famously line subduction zones. This is the origin of the Pacific Ring of Fire, a horseshoe-shaped belt of volcanoes and earthquakes that frames the ocean, all born from the water released by sinking plates. Meanwhile, right at the interface between the descending and overriding plates, a completely different kind of construction is underway. Imagine a colossal bulldozer scraping material off the top of the descending plate. That's essentially what forms the accretionary wedge. Sediments that had accumulated peacefully on the ocean floor for millions of years, along with fragments of the volcanic basalt itself, are scraped off, jumbled, and smashed against the edge of the continent. This mixture is anything but orderly. It's a chaotic, deformed, and fractured mess of rock known as a mélange, a French term meaning mixture. This material is subjected to intense pressure, shearing, and the initial stages of metamorphism, beginning its transformation from ordinary ocean floor into something new and resilient. This wedge acts as a sort of geological waiting room where the raw materials for future mountains are collected, processed, and prepared for their eventual journey upward. These subduction zones are truly nature's most powerful recycling centers, taking old ocean floor and beginning the intricate process of turning it into new continental real estate. But what happens to all that scraped-off material? It doesn't just vanish. Instead, it begins to accumulate in one of geology's most dramatic construction zones. Picture a colossal, slow-motion landslide happening over millions of years, where instead of dirt and rocks tumbling down, oceanic material is being pushed up and added to the edge of the continent. This is the accretion process, where the continental plate essentially grows fatter by stealing material from the descending oceanic plate. It's like a geological tax collector, taking a significant portion of the ocean floor's sedimentary and volcanic wealth before it can disappear into the mantle. This process builds what geologists call an accretionary-prism, a massive, wedge-shaped stack of intensely deformed rock that forms right at the tipping point where the oceanic plate begins its descent. Imagine taking layers of deep-sea mud, volcanic ash, sandy turbidites, and even chunks of solid basalt from the ocean floor, and then subjecting them to unimaginable pressure that folds, fractures, and stacks them like a deck of cards being shuffled by a giant. The rocks within these prisms tell clear stories of their marine origin. You'll find pillow basalts, those distinctive blob-shaped volcanic rocks that form when lava erupts underwater and instantly cools. There are beds of chert, a hard, fine-grained silica rock that forms from the accumulated skeletons of microscopic radiolarians that once drifted in the ocean currents. And you'll find limestone layers full of fossils of creatures that lived in ancient seas, now preserved high and dry within these chaotic stacks. Over millions of years, this accumulated material becomes permanently welded to the edge of the continent, substantially thickening the crust and changing its very composition. This isn't just adding a bit of extra real estate, it's fundamentally building the foundation upon which future mountains will rise. The accretion process provides the bulk, the raw volume of rock that will eventually be compressed, folded, and uplifted into spectacular peaks. Without this constant addition of material at convergent margins, our mountain ranges would be far less impressive, and the continents themselves would be thinner and geologically poorer. This represents the crucial first step in the ocean floor's incredible transformation from deep-sea abyss to towering mountain summit, setting the stage for the even more dramatic changes yet to come. Now, as these ocean floor materials are dragged downward or plastered onto continents, they enter a realm of unimaginable pressure and searing heat that fundamentally alters their very essence. This isn't just a simple change, it's a complete metamorphic rebirth, a mineralogical makeover forced upon the rocks by the extreme conditions deep within the earth. Picture a piece of ordinary basalt, the same rock that formed from lava at a mid-ocean ridge. As it's pulled into a subduction zone, the increasing weight of overlying rock creates pressures tens of thousands of times greater than our atmosphere, while temperatures soar to hundreds of degrees Celsius. Under these incredible conditions, the minerals within the basalt become unstable and begin to reorganize themselves into new, denser forms that are stable in this harsh new environment. The most dramatic transformation occurs when that familiar dark basalt, under these specific high-pressure but relatively low-temperature conditions, recrystallizes into a stunning blue rock called blue schist. This rock gets its name and its striking color from a mineral called glaucophane, which only forms in these unique subduction zone settings. If the journey continues even deeper, the rock undergoes yet another transformation, becoming an even denser rock known as eclogite. Eclogite is a beautiful and important rock, often described as the signature mineral assemblage of subduction zones. It's characterized by red garnet crystals set in a matrix of green pyrozene, creating a dramatic and almost jewel-like appearance. The formation of eclogite is a critical moment because its high density actually helps pull the oceanic plate downward, accelerating the subduction process in a powerful feedback loop. Meanwhile, the marine sediments that were scraped off and added to the accretionary wedge aren't left unchanged either. Those layers of deep-sea mud, microscopic skeletons, and limestone accumulate under tremendous pressure, baking and squeezing until they transform into an entirely new family of rocks. The fine clay particles recrystallize into sparkling micas, creating various types of schist that split easily along wavy, glittering plains. Limestone, which began as the accumulated shells of countless marine organisms, undergoes a dramatic transformation as well. Under heat and pressure, the calcite crystals within the limestone recrystallize and grow larger, interlocking with each other to form marble, the same beautiful rock that sculptors cherish and that adorns magnificent buildings worldwide. What's truly remarkable is that these metamorphic rocks don't just change randomly. They record their entire pressure-temperature history through their mineral assemblages. Geologists can read these rocks like a geological thermometer and pressure gauge. The specific minerals present and their chemical compositions tell scientists exactly how deep these rocks were buried and how hot they became during their journey. For instance, the presence of the mineral jadate in certain rocks indicates they experienced pressures equivalent to being buried at least 60 kilometers deep. This forensic mineralogy allows researchers to reconstruct the complete path these rocks traveled, from the ocean floor to the depths of the earth and back again. This metamorphic transformation isn't just an interesting side effect, it's absolutely essential for the creation of mountains. The process strengthens the rocks dramatically, making them far more resistant to deformation than their original sedimentary and volcanic forms. This new toughness allows them to withstand the incredible forces of continental collision without simply crumbling away. the rocks become harder, more coherent, and mechanically robust, exactly the properties needed to build the towering, durable peaks that will eventually form mountain ranges. This metamorphic makeover is nature's way of taking relatively weak ocean floor materials and forging them into the structural backbone of future continents, preparing them for their ultimate dramatic return to the surface where we can marvel at their incredible journey. So how exactly do these deeply buried rocks, forged under immense pressure and transformed into their metamorphic states, make the incredible journey back to the surface? The answer lies in a powerful combination of geological mechanisms working in concert, a kind of planetary elevator system that lifts what was once hidden into plain sight. The primary driver is continental collision, the grand finale of the tectonic dance. After an ocean basin has completely closed, the two continental masses finally meet. Since both are made of relatively light, buoyant rock, neither wants to subduct deeply into the dense mantle. Instead, the crust responds by crumpling, much like a car hood in a head-on collision. This massive compression thickens the crust dramatically, sometimes doubling its normal thickness. And just like an iceberg, the thicker this crustal root becomes, the higher it floats on the underlying mantle, pushing the entire mountain range upward in a process known as crustal thickening and isostatic uplift. But the work isn't done by collision alone. Erosion plays a surprisingly active and essential role in this uplift process. Think of it as a partnership between destructive and constructive forces. As wind, water, and ice tirelessly scour the landscape, they strip away material from the top of the growing mountains. This removal of weight triggers a response deep within the earth, governed by the principle of isostasy, the same concept that explains why a lightly loaded boat floats higher in the water than a heavily loaded one. As the erosional unburdening lightens the load, the underlying crust, which is still floating on the ductile mantle, rises upward to regain its equilibrium. This isostatic rebound effectively exhumes the deeper rocks, bringing them closer to the surface. In some mountain ranges, geologists have calculated that for every kilometer of rock eroded away, the crust rebounds upward by nearly 0.8 of a kilometer, a remarkable demonstration of this gravitational balancing act. Beyond these primary mechanisms, other more localized processes can also exhume deeply buried rocks, sometimes at astonishing speeds. In certain tectonic settings, particularly where continents are stretching apart, extensional faults can act like geological elevators. Large blocks of crust can drop downward along these faults, effectively making adjacent blocks appear to rise rapidly in relative terms, bringing high-pressure rocks up from depth. Another fascinating process is delamination, where the dense, lowermost part of the thickened crust actually peels away and sinks into the mantle. This removal of the dense anchor allows the remaining, lighter crust to bob upward much more rapidly, like a buoy released from its mooring. These alternative pathways help explain how some ultra-high-pressure rocks, which were buried to depths of over 100 kilometers, managed to return to the surface without being completely obliterated or melted on their long journey home. Together, these uplift mechanisms serve as Earth's intricate delivery system, ensuring that the incredible story written in these transformed ocean floor rocks is not lost forever to the depths, but is instead proudly displayed for us to discover and decipher. Now, if you really want to see the most spectacular, undeniable proof that ocean floors can become mountains, you need to look at one of geology's most incredible gifts, ophiolites. These are not just random rocks, they are complete, intact sections of ancient oceanic crust and the upper mantle that have been thrust up onto the continents, essentially stranding them high and dry for us to study. Imagine having a slice of the deep earth, a cross-section of an entire ocean basin, delivered right to your doorstep. That's exactly what an ophiolite is, a geological time capsule of the highest order. What makes them so special is their perfect textbook sequence. If you were to walk from the bottom of an ophiolite to its top, you would be taking a journey that replicates drilling straight down through an ocean floor. It starts at the very bottom with mantle rocks, primarily a dense green rock called peridotite. This is the material that the Earth's mantle is made of, and it's rarely seen on the surface unless an ophiolite brings it to us. Above that, you find layered gabbros. These are coarse-grained rocks that formed from magma cooling slowly in a large chamber beneath a mid-ocean ridge. Then comes one of the most distinctive features, the sheeted dike complex. This looks like a massive, organized stack of black, vertical walls. Each dike represents a single fracture that was filled with molten rock, which then cooled to form a solid wall, the very plumbing system that fed lava onto the ancient seafloor. Above these dikes, the story erupts onto the seafloor itself. Here we find magnificent pillow basalts. These are not your typical blocky lava rocks. They have beautiful, blob-like bulbous shapes that form in one of the most unique ways imaginable. When basaltic lava erupts under the immense pressure and cold temperature of the deep ocean, it doesn't flow. Instead, it instantly chills and forms a glassy skin, while more lava inside pushes out to form another blob, creating a continuous pile of these incredible pillow structures. It's a signature formation that screams eruption underwater. Finally, capping it all off are the deep-sea sediments, layers of chert, limestone, and mudstone that slowly, painstakingly settled on top of this volcanic landscape, often containing the fossilized remains of microscopic organisms that lived in the water column above. To see this in person is a geologist's dream, and there are famous locations around the world where you can do just that. The Seamail ophiolite in Oman is arguably the largest and most well-exposed example on Earth. It's a massive slab of ancient ocean floor that was abducted or thrust onto the Arabian Peninsula. You can literally drive across what was once the boundary between the mantle and the crust. Similarly, the Troodos Massif in Cyprus offers another world-class example, where the classic sequence is beautifully preserved and has been studied for decades. These sites are more than just scenic landscapes. They are fundamental to our understanding of plate tectonics. They provide the direct, tangible evidence that the theory is correct. We can point to these rocks and say, without a doubt, that this was the bottom of an ocean, and now it's part of a continent. They are the ultimate smoking gun in the story of how our dynamic planet constantly recycles itself, turning the deepest seabed into the highest peaks. This grand recycling of our planet's surface isn't a one-time event but a recurring drama that has played out again and again across the vast expanse of geological time. These major mountain-building episodes, known as orogenies, are the climactic chapters in Earth's story, each one a testament to the relentless power of plate tectonics. Think of an orogeny not as a single earthquake or volcanic eruption, but as an entire geological era of colossal construction, a multi-million-year period where continents collide, oceans close, and the very crust of our planet is crumpled and forged into breathtaking new landscapes. We are actually living within one of these monumental events right now. The Alpine Himalayan orogeny began roughly 50 million years ago when the Indian subcontinent, having broken away from the supercontinent Gondwana, went on a relentless northward journey across the ancient Tethys Ocean. Its dramatic collision with the underbelly of Asia didn't just create a few hills, it initiated the most spectacular mountain-building event of the modern era, one that is still forcefully lifting the Tibetan Plateau and the entire Himalayan range skyward at a rate of about 1 centimeter per year. Every time you see an image of Mount Everest, you are looking at the active, ongoing work of an orogeny. a process that is continually resurrecting the limestone and marine sediments of that long-vanished ocean to the top of the world. But to truly appreciate the cyclical nature of our planet, we must look back to even older orogenies whose worn-down roots tell equally impressive stories. The Appalachian Mountains that stretch along the eastern North American seaboard may seem gentle and ancient today, but they are the weathered remnants of a once mighty Himalayan scale range. They were born from a series of colossal collisions hundreds of millions of years earlier during the Paleozoic era, the closing of the ancient Iapetus Ocean, which once separated ancestral North America from other landmasses, plastered enormous slices of its ocean floor onto the continent's edge. The evidence is everywhere for those who know how to look. Slivers of ancient seafloor rock called ophiolites are preserved from Alabama to Newfoundland, and marine fossils can be found in rocks now thousands of feet above sea level, silent witnesses to a vanished world. Across the Atlantic, the story repeats itself. The Caledonian orogeny, which sculpted the landscapes of Scotland, Norway, and parts of Greenland, is essentially the other half of the Appalachian story. These mountains were once part of the same continuous range, a mighty spine that formed when the ancient continents of Laurentia and Baltica smashed together, closing yet another ocean basin. The process is always the same, a familiar geological recipe that has been followed time and again. It starts with the formation of a new ocean basin as continents rift apart. That basin widens for tens of millions of years, its floor accumulating layers of sediment. Eventually, the forces driving the plates shift, and subduction begins, slowly consuming the ocean floor and pulling the continents back toward each other. The final, breathtaking act is the continental collision itself, the slow, unstoppable crash that crumples the margins of both continents, welding them together and uplifting all the accumulated oceanic material into a new mountain range that stands as a permanent monument to the ocean that once was. This repetitive pattern reveals a profound truth about our planet. Earth operates in cycles that transcend human comprehension. Oceans are born, they live, and they die, only to have their remains enshrined in the continents they once separated. The very ground beneath our feet is a palimpsest, a layered record of these ancient cycles written in stone. Each orogeny, from the youngest peaks in the Himalayas to the ancient, rounded folds of the Appalachians, confirms that the resurfacing of ocean floors is not a rare fluke but a fundamental, rhythmic process in the life of our dynamic planet. And when we talk about monumental proof of this incredible planetary process, there is simply no greater, more dramatic example than the Himalayas. This colossal mountain range, often called the roof of the world, is more than just a breathtaking landscape. It is the ultimate geological crime scene, and the evidence is written everywhere you look. The entire story begins with the Tethys Ocean, a vast, ancient sea that once separated the supercontinent of Gondwana, which included modern-day India, from the rest of Asia. For over 150 million years, this ocean was home to a thriving marine ecosystem, its floor steadily accumulating layers of limestone from the skeletons of countless sea creatures, along with sediments washing in from distant lands. Then, around 50 million years ago, the stage was set for an unprecedented collision. The Indian plate, having broken away from Gondwana, was racing northward at a geologically breakneck speed, and it carried the entire floor of the Tethys Ocean on its back. There was nowhere for the ocean to go but up. The most iconic piece of evidence for this is found at the very top of the world. The summit pyramid of Mount Everest, the highest point on our planet at over 29,000 feet, is not made of some exotic volcanic rock. It is composed of a gray limestone that is absolutely packed with the fossilized remains of crinoids, brachiopods, and other marine organisms that lived in a warm, shallow sea. Think about the profound implication of that for a moment. The literal apex of Earth's topography, a place of unimaginable cold and thin air, was once the bottom of a warm, sun-dappled ocean. Those fossils are not just decorative, they are the undeniable, irrefutable signature of the rock's origin. Every climber who stands on that summit is standing on a former seafloor, a fact that transforms a physical achievement into a journey through deep time. But the evidence doesn't stop at the summit. Running along the entire length of the Himalayas is a geological feature known as the Indus-Tsangpo Suture Zone. The word suture is perfectly chosen. It is the scar, the stitch mark, where the Indian and Eurasian plates were welded together. Within this zone, geologists have found some of the most spectacular ophiolite sequences on the planet. These are massive, crumpled slabs of the Tethyan ocean floor that were scraped off during the collision and thrust up onto the continent. You can hike through these areas and see the classic sequence: the dark, dense mantle rocks, the layered gabbros that cooled deep beneath an ancient mid-ocean ridge, the dramatic sheeted dike complexes that served as undersea lava conduits, and the iconic pillow basalts that formed when that lava erupted onto the cold seafloor. It's a complete cross-section of an entire oceanic plate delivered to your feet. For a geologist, working in the Himalayas is the closest one can get to time travel. You can put your hand on a rock that once lay at the bottom of a vanished ocean, feel the texture of the pillow basalts, and examine the delicate fossils in the limestone. You can trace the incredible folds and faults that contorted these rocks during the collision, seeing the physical manifestation of titanic forces. The Himalayas are not a static monument. They are an active, dynamic laboratory where the process of ocean floor resurfacing is still ongoing, with the mountains continuing to rise by a few millimeters each year. This majestic range is the ultimate testament to the power of plate tectonics, a permanent and awe-inspiring reminder that the highest peaks are built from the deepest seas. While the Himalayas offer a spectacular story of continental collision, the Andes present a completely different, yet equally fascinating, chapter in our geological saga. Here, the process isn't about a single, cataclysmic crash between two continents, but rather a relentless, grinding, and continuous tectonic push that has been ongoing for over 200 million years. The primary engine is the inexorable subduction of the dense Nazca Plate as it dives beneath the massive South American plate. This creates a very different kind of mountain chain, one dominated by a nearly continuous line of explosive volcanoes, but one that also incorporates vast amounts of ancient ocean floor in its own unique way. The evidence of this oceanic incorporation is written across the western face of the entire continent. Perhaps the most visually stunning examples are the immense marine terraces that stair-step their way up the mountainsides in countries like Peru and Chile. These are not mere hills, they are former beaches and wave-cut platforms, now stranded thousands of meters above the modern Pacific Ocean. Each flat terrace represents a moment in time when that piece of land was at sea level before being hoisted upward by the relentless tectonic forces. Geologists can literally walk these ancient shorelines, studying the shells and fossils embedded within them to not only date the terraces, but also to calculate precise rates of uplift. It's like having a giant geological tape measure, showing us that parts of the Andes have been rising at rates of several millimeters per year for millions of years, relentlessly pushing the ghosts of ancient coastlines into the clouds. But the story goes much deeper than these surface features. Within the complex internal anatomy of the Andes, geologists have discovered belts of blue schist, those telltale high-pressure, low-temperature metamorphic rocks that act as a definitive fingerprint of subduction. Their presence confirms that slices of the oceanic plate were dragged to significant depths before being somehow exhumed and stitched into the fabric of the mountains. Furthermore, there are numerous accreted terrains, which are essentially large, fault-bounded packets of rock that have a different geological history than the continent they're now attached to. Many of these are identified as fragments of ancient oceanic plateaus, seamounts, or even island arcs that were riding on the Nazca Plate like geological passengers. Instead of subducting into the mantle, these thicker, more buoyant chunks were too stubborn to sink. They were scraped off and plastered onto the edge of South America, adding width and volume to the continent and becoming a permanent part of the Andean backbone. This continuous, non-collisional style of mountain building dramatically expands our understanding of how ocean floors resurface. The Himalayas show us the spectacular end result of an ocean closing completely. The Andes, in contrast, demonstrate that you don't need a final continental collision to build a massive mountain range and incorporate oceanic material. Here, the ocean is still very much present right next door, and the process is ongoing, active, and observable. It's a slower, more methodical form of construction, where the mountain chain grows vertically through volcanic activity fed by the subducting slab, and it grows laterally through the steady accretion of these oceanic fragments. This alternative mechanism proves that the resurfacing of ocean floors is a versatile and widespread process, capable of creating some of Earth's most dramatic landscapes through both dramatic collisions and persistent, relentless pressure. Now, let's journey to the heart of Europe, where the majestic Alps stand not merely as a picturesque backdrop for skiers and hikers, but as one of the most complex and revealing geological storybooks on the planet. Unlike the more straightforward collisions that built other ranges, the Alps are a magnificent geological crossroads, an intricate jigsaw puzzle assembled from the shattered remnants of not one, but several ancient oceans. This mountain chain is the direct result of a slow-motion, multi-million-year convergence between the African and European continental plates, a colossal tectonic embrace that squeezed shut the oceanic domains that once lay between them. The most significant of these vanished seaways was the Tethys Ocean, a vast, ancient body of water that once separated the supercontinents of Laurasia and Gondwana. But the story is even richer than that. Nestled within the broader Tethyan realm were smaller, subsidiary ocean basins like the Panionic Ocean. As the African plate pushed northward, these oceans didn't just close neatly. Instead, their floors were subjected to an incredibly complex series of subductions, collisions, and continental fragments jostling for position. The result is a geological mosaic where slivers of continental crust are interleaved with thick slices of oceanic material, all folded, faulted, and stacked upon one another in a breathtaking display of tectonic force. Perhaps no single peak better symbolizes this dramatic history than the iconic Matterhorn. Its stark, pyramidal summit is instantly recognizable, but its true majesty lies in its composition. That famous peak is not built from a single block of rock. It is a tectonic layer cake. Its lower sections are composed of ancient continental basement rocks, the deeply rooted foundation of the European margin. But as your eye travels upward, you are literally moving through geological time. The upper parts of the mountain include thick layers of sedimentary rock, limestones and marbles, that were originally deposited as calcareous ooze and coral reefs on the floor of the Tethys Ocean. These marine sediments were then scraped off, folded into incredible nappes, huge, carpet-like sheets of rock that were thrust over one another for dozens of miles, and finally hoisted to their present dizzying altitude. For a geologist seeking the ultimate classroom, the Zermatt-Soz zone in Switzerland is an unparalleled destination. Here, the process of ocean floor resurfacing is laid bare in spectacular fashion. Winding valleys and towering cliffs expose some of the most complete and beautifully preserved ophiolite sequences anywhere in the world. You can stand in one spot and see the entire story. The dull green sheen of mantle peridotite, the coarse-grained gabbro that crystallized deep beneath an ancient mid-ocean ridge, the dramatic black walls of the sheeted dike complex that fed lava to the surface, and finally, the bulbous, unmistakable forms of pillow basalts that erupted onto the cold seafloor. These rocks didn't just get gently lifted. They were subjected to immense pressure, transforming the basalt into dense, shimmering eclogite, a rock that tells of a journey to depths of over 60 kilometers before making its return trip to the surface. What makes the alpine example so special for scientists is the incredible level of detail preserved in the deformation structures. By meticulously mapping the folds and faults, geologists can act like detectives reconstructing a crime scene, piecing together the precise directions and magnitudes of the forces that shaped these mountains. They can trace individual rock layers as they are contorted into intricate folds, see where massive thrust faults have shoved older rocks on top of younger ones, and understand how the entire stack was subsequently stretched and pulled apart as it rose. This intricate folding and faulting is the very mechanism of the resurfacing process, the physical manifestation of how ocean floor can be crumpled, stacked, and ultimately delivered back to the light of day. The Alps, in all their complexity, stand as a timeless testament to the dynamic and often beautifully chaotic forces that continuously reshape our planet. Traveling east from the young, jagged peaks of the Alps, we find ourselves in a landscape that tells a much older, more patient story of geological resurrection. The Appalachian Mountains, stretching like a gentle, forested spine from Alabama to Newfoundland, may not boast the dramatic vertical relief of the Himalayas, but they possess a profound and weathered wisdom. These are mountains that have seen empires of rock rise and fall, and within their rounded folds and quiet valleys, they preserve what might be the most compelling evidence on Earth that the cycle of ocean floor resurfacing is one of our planet's most ancient and enduring processes. Their current modesty is a disguise. They are the worn-down stumps of a mountain range that once rivaled the Himalayas in their grandeur, a titan worn smooth by 500 million years of wind and rain. The true story of the Appalachians is written in the rocks of its core, particularly within the Blue Ridge and Piedmont provinces. To hike through these regions is to walk across the graveyard of not one but several ancient oceans. The most significant of these was the Iapetus Ocean, a vast Paleozoic sea that once separated ancestral North America from other ancient continents. As this ocean began to close its floor, a landscape of volcanic ridges and sediment-filled abyssal plains was destined for recycling. Today, the evidence is scattered throughout the hills. Geologists have identified numerous ophiolite fragments, which are the mangled and metamorphosed remains of that Iapetan oceanic crust. You won't find the perfect textbook sequences of Oman here. Time and immense tectonic violence have broken them into pieces, but their identity is unmistakable. In places like the Baltimore Mafic complex in Maryland or certain rocks in the North Carolina Piedmont, you can still find the signature rocks, chunks of serpentinized mantle peridotite, metamorphosed gabbro, and even hints of pillow basalts, all telling a silent story of a long-vanished sea. But the closing of the Iapetus was just the first act. Another ocean, the Rake, also played a crucial role in building this range. The collisions that assembled the supercontinent Pangaea were not a single, tidy event, but a long, complex series of continental fragments called terranes slamming into the eastern coast of North America. Imagine a series of geological freight trains, each carrying its own cargo of oceanic crust and sediment, crashing slowly into the continent. With each impact, more material from the ocean floors was scraped off, accreted, and smashed onto the growing margin of the continent. This process added immense width to the eastern seaboard, building the Appalachians outwards, piece by piece, terrain by terrain. The rocks from these accreted terrains are often highly deformed and metamorphosed, a chaotic mixture of volcanic and sedimentary rocks that clearly originated elsewhere, far out in those ancient oceans. Perhaps the most awe-inspiring evidence of the incredible journey these rocks undertook is found in the high-pressure metamorphic rocks discovered throughout the range. In certain locations, such as parts of Vermont and western North Carolina, geologists have found rocks like blue schist and eclogite. These are the mineralogical equivalent of a black box recorder from a deep Earth mission. The presence of the blue mineral glaucophane in blue schist is a definitive sign that these rocks were subjected to immense pressure but relatively low temperatures, the exact conditions found in a subduction zone. Some of these rocks were dragged down to depths of over 50 miles, to the very brink of the mantle, before somehow making the arduous journey back to the surface. Their existence in the Appalachians is nothing short of miraculous. It proves that these now tranquil hills were once the site of tectonic forces so powerful they could drag seafloor to the edge of the underworld and then exhume it again. This ancient history transforms our understanding of the planet's timeline. The Himalayas, for all their drama, represent a relatively recent chapter in Earth's story. The Appalachians show us that this magnificent recycling program has been operating for at least 500 million years. They are a time-tested example, a proven model of how ocean floors are not merely transient features but are fundamental building blocks in the permanent construction of continents. Every step on the Appalachian Trail, therefore, is a walk across the solidified remains of ancient, forgotten oceans, a testament to the fact that even the most solid and enduring landscapes are built from the most ephemeral of beginnings. So how do scientists actually know that a particular chunk of rock high in the mountains was once at the bottom of an ancient ocean? It's not like these rocks come with a label attached. Unraveling this deep time detective story requires a sophisticated geological toolkit, a blend of old-school field observation and cutting-edge laboratory science that together reveal the hidden origins of these transformed landscapes. It all begins with the most fundamental tool in geology, the trained human eye. Before any high-tech analysis happens, geologists head into the field with a map, a compass, a rock hammer, and a notebook. They meticulously trace out rock layers across rugged terrain, noting the exact sequence of different rock types and how they relate to each other. They're looking for specific patterns, like the classic ophiolite sequence of mantle rock, gabbro, sheeted dikes, and pillow basalts, even if it's been tilted, folded, or broken by faults. They document the structures, the folds that show how the rocks were compressed, the faults that show where they were sliced apart, and the way different rock units are stacked together. This careful field mapping provides the essential context, the large-scale story that guides all subsequent investigation. It's the foundation upon which the entire investigation is built. Once interesting rocks are identified in the field, the next step moves to the laboratory bench and the microscope. Geologists create incredibly thin slices of rock, so thin that light passes through them, and examine them under a petrographic microscope. This reveals a hidden universe of minerals and textures invisible to the naked eye. It's here that they can identify the definitive fingerprints of an oceanic origin. Finding a mineral like glaucophane, which gives blue schist its distinctive color, is a major clue. This mineral only forms under the high-pressure, low-temperature conditions of a subduction zone. Similarly, spotting the olive-green crystals of olivine, a mineral common in Earth's mantle, strongly suggests the rock is a piece of the upper mantle from an ophiolite complex. The microscope also reveals the rock's texture, how the mineral grains interlock, their size, and any deformation they've endured. This micro-scale analysis confirms the story the field mapping began to tell, providing undeniable mineralogical evidence of a dramatic journey. The investigation then goes molecular with geochemical fingerprinting. Using sophisticated instruments like mass spectrometers, scientists vaporize tiny bits of rock to analyze their precise chemical and isotopic composition. Different geological environments leave distinct chemical signatures. Rocks that formed at a mid-ocean ridge, for instance, have very specific ratios of rare earth elements that differ from rocks that formed on a continent or in a volcanic arc. Isotope geochemistry is particularly powerful. The ratio of strontium isotopes or neodymium isotopes in a rock acts like a geological birth certificate, tracing the rock's source material back to the Earth's mantle, which is the ultimate origin of all oceanic crust. This geochemical evidence is often the smoking gun that confirms a rock's oceanic heritage beyond any reasonable doubt. Another brilliant technique taps into Earth's ancient magnetic field. When iron-rich minerals in molten lava cool down at a mid-ocean ridge, they freeze in place, aligning themselves with the planet's magnetic field at that exact moment in time. Because Earth's magnetic field has reversed its polarity hundreds of times throughout history, this creates a symmetrical pattern of magnetic stripes on the seafloor. When a piece of this seafloor is later uplifted into a mountain, a paleomagnetist can drill out small core samples, measure the preserved magnetic direction in the lab, and determine the original latitude at which the rock formed. Finding that a rock in a temperate mountain range originally cooled at a tropical latitude is a clear indicator that it has traveled thousands of miles from its birthplace. Finally, if the oceanic rocks are associated with sedimentary layers, paleontologists provide the final piece of the puzzle. The deep-sea sediments that accumulate on the ocean floor are filled with the microscopic skeletons of single-celled organisms like radiolarians and foraminifera. These creatures are highly sensitive to water temperature, depth, and age. By identifying the specific species present in the sedimentary rocks attached to the volcanic ones, scientists can pinpoint the exact time period when the ocean floor was formed and even determine the depth and environmental conditions of that long-vanished ocean. It's this powerful combination of mapping, microscopy, chemistry, physics, and biology that allows geologists to confidently point to a mountain and declare with absolute certainty, this was once the bottom of the sea. Yet for all the incredible power of tectonic uplift, these resurrected ocean floors would remain forever hidden from our view without the patient, persistent work of another geological force. Think of erosion not as a destructive process, but as nature's master sculptor and ultimate revealer. While the titanic forces of collision and subduction provide the incredible vertical lift, it is erosion that does the meticulous work of stripping away the overburden, carefully unwrapping the geological presence that tectonics has delivered. This partnership between the builder and the excavator is what ultimately allows us to read the story written in the rocks. Consider the world's great river gorges, like the Kali Gandaki cutting through the Himalayas or the Indus River slicing through the mountains of Pakistan. These are not just scenic wonders, they are the planet's most profound natural cross-sections. As these powerful rivers carve downward, they act like a colossal geological saw, cutting through thousands of meters of rock and exposing a vertical timeline of Earth's history. A geologist floating through the Grand Canyon sees layers representing over 1 billion years of history. Similarly, in these mountain river gorges, we can see how the slices of ancient ocean floor, the ophiolites and high-pressure metamorphic rocks, are intricately folded and faulted against the older continental rocks. These dramatic exposures show us the very architecture of the collision, revealing how the oceanic material was emplaced, providing a three-dimensional diagram that would otherwise remain a complete mystery. In colder, higher latitudes, a different kind of erosional artist takes over. Glaciers, with their immense weight and slow, grinding movement, are nature's most effective surface planers. As they advance and retreat over millennia, they scour the landscape down to its very bones, scraping away all the soft, weathered material and polishing the hard, resistant bedrock to a brilliant shine. In places like the Alps or the fjords of Norway, glacial erosion has done more than just reveal the rocks. It has created the entire dramatic topography of sharp peaks and deep U-shaped valleys that make these landscapes so iconic. This process doesn't just expose the rock, it accentuates the differences between rock types. Softer schists might be carved into valleys, while more resistant layers of marble or tough, metamorphosed basalt stand out as ridges and peaks, creating a topographic map that directly reflects the geological structure and making it easier for scientists to interpret the complex history. Even on a smaller, more subtle scale, weathering plays a crucial role in this revelation. When rain, wind, and daily temperature fluctuations attack a rock surface, they don't do so uniformly. Different minerals within the rock respond differently. Softer minerals might dissolve or crumble away, while harder minerals remain, creating a textured surface that highlights the rock's composition and structure. This differential weathering can expose intricate folds, reveal mineral banding, or make fossils pop out in high relief. It's the reason we can sometimes see the beautiful, bulbous shapes of pillow basalt so clearly on a weathered cliff face. The softer matrix around them has eroded away, leaving the more resistant lava pillows standing in proud, three-dimensional relief, telling their story of underwater eruption to anyone who knows how to look. The true magic lies in the synergy between these forces. Tectonic uplift provides the raw material and the vertical relief, creating the potential energy that drives erosion. The higher the mountains are pushed, the steeper the slopes become, and the more aggressively rivers cut and glaciers scour. Erosion, in turn, doesn't just passively reveal what's there, it actively influences the tectonic process itself. By stripping away immense weight from the top of the mountain range, erosion triggers isostatic rebound, causing the entire crust to float upward higher, which in turn brings even deeper rocks closer to the surface in a beautiful feedback loop. This relentless natural excavation is what grants us access to the most profound geological treasures, the ultra-high pressure rocks that journeyed to the mantle and back, the perfect ophiolite sequences, the fossils from vanished seas. Without the patient, persistent work of erosion, these stories of ancient oceans would remain buried forever, hidden secrets of our dynamic planet. To truly grasp the monumental process we've been exploring, we must shift our perspective to a timescale that defies everyday human experience. We're not talking about centuries or even millennia here, but deep geological time spanning tens to hundreds of millions of years. This is the patient, relentless rhythm of our planet's recycling program, a timescale where mountains rise and fall like slow breaths. Consider the journey of a single piece of oceanic crust. It begins its life at a mid-ocean ridge, fresh from the mantle, and then embarks on an epic voyage across the ocean basin. This transit alone can take a staggering 100 to 200 million years, a period longer than the entire existence of the Atlantic Ocean. During this immense span, it steadily accumulates layers of sediment, recording the history of an entire era as it slowly drifts toward its destiny. When this aging seafloor finally reaches a subduction zone, the next phase of its transformation begins, the process of subduction and accretion, where the plate dives beneath a continent and has its surface materials scraped off unfolds over another several million years. This isn't a sudden event but a continuous, grinding process where rocks are subjected to increasing pressure and heat, gradually metamorphosing into new mineral forms. Then comes the uplift stage, where these deeply buried rocks begin their return journey to the surface. Depending on the intensity of the continental collision and the efficiency of erosion, this exhumation process can take yet another few million to tens of millions of years. The entire cycle, from formation at a ridge to exposure on a mountain peak, might easily span 250 million years or more. To put that in perspective, the last time a particular piece of rock now in the Himalayas was at the Earth's surface, the dinosaurs were just beginning their domination of the planet. This incredible timescale explains why we find evidence of this process preserved in mountain ranges of vastly different ages. The young, still-growing Himalayas, less than 50 million years old, show us the process in a relatively early stage. The Alps, dating back to a collision that began around 30 million years ago, represent a middle-aged example. Meanwhile, the ancient Appalachians, whose origins stretch back over 480 million years, show us the final, weathered-down results of this cycle. Each range preserves a snapshot of Earth's dynamic history from different geological eras. The rocks in the Appalachians tell stories of oceans that vanished before complex life even crawled onto land, while the Himalayas record the closure of an ocean that existed alongside the early mammals. This variation in age creates a rich geological archive, allowing scientists to compare how the process worked under different conditions throughout Earth's history. Understanding these vast timeframes is essential because it changes how we perceive stability and change on our planet. The ground beneath our feet feels permanent and solid, but in geological terms, it's in constant, albeit extremely slow, motion. The forces that drive this resurfacing mantle convection, plate movement, continental collision operate with such immense power that they can move continents, but they do so at speeds barely perceptible over a human lifetime. This perspective fosters a profound appreciation for the gradual but unstoppable forces that shape our world. It reminds us that the mountains we see today are not permanent features but temporary expressions of Earth's dynamic interior, destined to be worn down and recycled into future landscapes yet unimaginable. This grand temporal scale is the fundamental context without which the story of ocean floors becoming mountains remains incomplete, reducing our epic planetary saga to merely a curious anecdote. Beyond their breathtaking beauty and profound scientific value, these resurrected ocean floors hold a very practical and often overlooked significance. They are treasure troves of some of the planet's most vital mineral resources. This isn't a coincidence, it's a direct consequence of the unique geological processes that forged them deep beneath ancient seas. When we trace the origins of many of the metals and materials that power our modern world, the trail often leads us right back to these uplifted slices of oceanic crust, making them not just windows into the past but cornerstones of our present and future economy. The story begins at the very birthplace of the ocean floor itself, the mid-ocean ridge. Here, in the pitch-black depths, superheated water circulates through cracks in the young, hot oceanic crust. This water acts as a powerful natural solvent, leaching valuable metals like copper, zinc, lead, gold, and silver from the surrounding rocks. When this mineral-rich, superheated fluid erupts back onto the cold seafloor, it instantly cools, precipitating its metallic cargo around the vent opening. This creates spectacular chimney-like structures known as black smokers, which over thousands of years build up massive sulfide deposits on the ocean bottom. When this piece of seafloor is later scraped off and uplifted into a mountain range, these ancient hydrothermal vent systems become what miners call volcanogenic massive sulfide deposits, or VMS. These are among the world's most important sources of base and precious metals. The famous mines of the Iberian Pyrite Belt in Spain and Portugal, which have been producing copper for over 3,000 years since the time of the Romans, are classic examples of these fossilized hydrothermal systems, now sitting high and dry within a mountain chain that was once an ancient ocean. But the mineral wealth doesn't stop there. The lower sections of ophiolite sequences, those pieces of the Earth's mantle that were brought to the surface, host an entirely different suite of critical resources. Within the mantle rocks, particularly a rock type called dunite, we find rich concentrations of chromite. This isn't the decorative stone you might be thinking of. Chromite is the sole ore of chromium, a metal absolutely essential for manufacturing stainless steel and for use in superalloys for jet engines and industrial applications. Some of the world's most significant chromite deposits are found within ophiolites, like those in the Shetland Islands of Scotland or in the Urals of Russia. These same mantle rocks can also be the source of platinum group elements, incredibly rare and valuable metals crucial for catalytic converters in vehicles and various high-tech industrial processes. Another mineral historically mined from these altered mantle rocks is asbestos, specifically the chrysotile variety, which formed when water interacted with the olivine in the peridotite. While its use is now heavily restricted due to health risks, its presence is a clear marker of these deep earth rocks. The sedimentary layers that capped the ancient ocean floor also contribute significantly to our resource base. Those layers of deep sea chert and limestone can become host rocks for phosphorite deposits. These form from the concentrated skeletons of countless microorganisms that lived in the water column, creating rich sources of phosphorus, which is absolutely fundamental for manufacturing agricultural fertilizer that helps feed the global population. Furthermore, the organic rich muds that accumulated in quiet, deep water environments, far from the diluting effects of continental sand and silt, can over millions of years and under the heat and pressure of burial, transform into the source rocks for hydrocarbons. While we typically don't drill for oil and gas in the complex, deformed hearts of mountain ranges, understanding that these rocks originated on an ancient ocean floor helps geologists predict where similar, less deformed source rocks might be found in adjacent sedimentary basins. This practical economic dimension transforms the way we view these geological wonders. For exploration geologists, understanding the origin and distribution of these resurfaced ocean floor materials is like having a detailed map to buried treasure. Knowing that a particular mountain range contains a well-preserved ophiolite complex immediately flags it as a highly prospective area for chromite, platinum, or massive sulfide deposits. They can use their knowledge of the classic ophiolite sequence to guide their search, focusing their efforts on the specific layers where certain minerals are most likely to be concentrated. This connection between pure scientific research and real-world application is a powerful reminder that investigating Earth's deep processes isn't just an academic exercise. It directly fuels our technological society, provides the raw materials for innovation, and underscores the incredible value of preserving and studying these magnificent geological archives. The very mountains that inspire us with their beauty also quietly underpin the infrastructure of our modern lives, a hidden legacy of the ancient oceans from which they came. These uplifted ocean floor materials are far more than just ancient stones. They are time capsules of the highest order, preserving intricate details about the environments in which they formed. When geologists examine these rocks, they are essentially acting as crime scene investigators for the planet, piecing together clues to reconstruct entire worlds that have long since vanished. Every layer, every mineral, and every texture holds a piece of the puzzle, allowing us to read the history of Earth's oceans, climates, and life forms with astonishing clarity. This process of paleo-environmental reconstruction transforms cold, hard rock into a dynamic narrative of our planet's deep past. Take, for instance, the delicate layers of radiolarian chert often found nestled within these sequences. This hard, fine-grained rock, which often fractures with a sharp, conchoidal edge, is composed almost entirely of the microscopic silica skeletons of radiolarians, tiny, single-celled plankton that drifted in the sunlit upper waters of ancient oceans. When these organisms died, their intricate skeletons settled slowly through the water column, accumulating on the deep seafloor like a continuous rain of microscopic glass. The sheer abundance of their preserved remains indicates periods of high biological productivity in the surface waters. But scientists can go even further. By identifying the specific species of radiolarians present, they can pinpoint the exact geological age of the rock because these creatures evolved rapidly over time. Furthermore, the chemical composition of their shells can be analyzed to determine the temperature and even the acidity of the ocean water they lived in millions of years ago. A single chip of chert, therefore, becomes a detailed logbook of biological activity, ocean chemistry, and geologic time. Equally revealing are the layers of limestone that frequently cap these oceanic sequences. These rocks begin as the accumulated remains of countless marine organisms, not just microscopic plankton like foraminifera, but also fragments of shells, corals, and other carbonate-secreting life. When this material is uplifted into a mountain, the limestone becomes a fossilized snapshot of the marine ecosystem. The types of fossils present tell a vivid story. An abundance of reef-building organisms suggests a warm, shallow, tropical environment, while a dominance of deep water forms indicates a dark, cold abyssal plain. The very texture of the limestone, whether it is fine-grained mud or coarse-grained rubble, speaks volumes about the energy of the environment, whether it was a quiet deep water basin or a turbulent shoreline battered by waves. By studying the ratios of different isotopes of oxygen locked within the calcium carbonate, geochemists can even calculate the precise temperature of the ocean when those creatures were alive, allowing them to chart the climate fluctuations of periods long before humans walked the Earth. The volcanic components of the ocean floor, particularly the iconic pillow basalts, offer a different but equally crucial set of clues. These distinctive blob-shaped structures, which look like a pile of stone pillows, form in one way and one way only, when lava erupts directly onto a cold, deep ocean floor. The rapid chilling creates the unique rounded forms and a glassy outer rind. The size and shape of the pillows can tell volcanologists about the viscosity of the lava and the rate of eruption. More importantly, the chemistry of the basalt itself is a direct fingerprint of the mantle source from which it melted. By analyzing its elemental composition, scientists can determine whether the lava erupted at a fast-spreading mid-ocean ridge, a slower-spreading ridge, or perhaps even at an off-axis seamount, painting a detailed picture of the volcanic geography of the ancient seafloor. Beyond the rocks themselves, the associated sedimentary layers act as a record of continental erosion. Thin layers of mudstone or sandstone interbedded with the cherts and limestones often contain mineral grains like zircon. These incredibly durable minerals can be dated with extreme precision, revealing the age of the distant continents that were being eroded at the time. The composition of these sand grains tells us what kinds of rocks were exposed on those ancient landmasses, whether there were towering granite mountain ranges, vast volcanic plateaus, or rolling hills of metamorphic rock. This allows geologists to reconstruct not only the ocean basin, but also the topography and geology of the continents that surrounded it, which may have themselves been completely destroyed by later tectonic events. This meticulous detective work, combining field observation with advanced laboratory analysis, allows scientists to assemble surprisingly complete and vivid portraits of these lost worlds. We can know the depth and temperature of an ocean that vanished 50 million years ago, understand the productivity of its surface waters, identify the volcanic activity that built its floor, and even characterize the continents that bordered it. These resurrected ocean floors are therefore the closest thing we have to a time machine, providing page after page of Earth's autobiography, written not in ink but in stone and fossil. While we can't actually watch a mountain range rise before our eyes in real time, our planet provides us with incredible living laboratories where this very process is actively underway, playing out in slow motion right now. These modern tectonic settings are the closest we can get to time travel, offering a front-row seat to the same forces that built the Alps and the Himalayas, but happening today, right beneath our feet and oceans. We don't need to imagine what an ancient subduction zone looked like. We can point to active ones like the Mariana Trench in the Western Pacific or the Cascadia subduction zone off the coast of the Pacific Northwest. These are the dramatic, real-world stages where the foundational work of future mountain building is currently in progress, giving scientists an unprecedented opportunity to observe the process from its earliest stages. The true revolution in our understanding comes from the sophisticated technology that acts as our window into this hidden world. Advanced seismic imaging techniques, similar to a geological CT scan, allow us to peer deep beneath the seafloor and map the structures that are forming in 3 dimensions. These images reveal the accretionary prisms in stunning detail, the chaotic, wedge-shaped piles of sediment and rock that are actively being scraped off the descending oceanic plate and added to the edge of the continent. We can see the faults forming, the layers folding, and the entire complex structure growing incrementally with each small earthquake. Simultaneously, precise seafloor mapping using multi-beam sonar systems paints a detailed picture of the ocean bottom, revealing the massive scale of these features, from the deep trenches themselves to the subtle bumps and ridges that mark the outermost edge of the growing continental margin. On land, a network of incredibly sensitive GPS stations tells another crucial part of the story. These instruments are not for navigation. They are measuring the slow, relentless creep of the Earth's crust with millimeter-level precision. Stations on the North American plate, for instance, are slowly being compressed, bulging upward and moving eastward as the Juan de Fuca plate dives beneath it along the Cascadia margin. This constant, precise monitoring allows scientists to calculate the exact rate of convergence, the speed at which the ocean floor is being consumed and the continent is being deformed. These measurements are the hard data that feed into computer models, helping us forecast the tectonic future of these regions and understand the immense forces that, over millions of years, will warp this landscape into a new mountain range. The immense value of studying these active zones is that they provide the key to interpreting the fossilized, often highly deformed rock record we find in ancient mountain belts. It's the difference between studying a living, breathing animal and trying to reconstruct one from its bones. A geologist examining a complex, folded rock formation in the Appalachians can look at the actively deforming accretionary-prism off the coast of Japan and think, aha. This is what that must have looked like before it was fully uplifted and eroded. These modern analogs help us decode the sequence of events, understand the types of deformation that occur, and identify the subtle features in ancient rocks that signify specific processes. They turn abstract theory into observable reality. This ongoing activity provides the ultimate proof that the grand geological cycle is not a thing of the past. The resurfacing of ocean floors is a continuous, dynamic process that is shaping our planet at this very moment. The ocean floor that is forming today along the East Pacific Rise will, one day in the distant future, be destined for its own journey into a trench and eventual resurrection in a mountain range yet to be named. While the timescales are far too vast for us to perceive without our most advanced instruments, the process is unceasing. These modern subduction zones are our planet's current construction sites, where the raw materials for future continents are being gathered and assembled, continuing the billion-year-old story of Earth's relentless self-renewal. This incredible geological recycling process does far more than just reshape our planet's surface. It actively engineers Earth's very climate, creating a powerful feedback loop between the rocks below and the skies above. When we see these majestic mountain ranges, we're looking at more than just uplifted ocean floor. We're witnessing colossal climate control systems that have been regulating global temperatures and weather patterns for millions of years. The connection begins with something as simple yet profound as rain. As prevailing winds carrying moisture from the oceans encounter a massive mountain barrier, they have no choice but to rise. This ascent cools the air mass, forcing it to release its moisture as precipitation on the windward side of the range. This creates lush, rainy environments like the temperate rainforests of the Pacific Northwest, which owe their existence to the presence of the coastal mountains. But on the opposite, leeward side, a very different story unfolds. The now dry air descends, warming up and creating arid rain shadows. The stark difference between the green, humid western slopes of the Andes and the bone-dry Atacama Desert to the east is a dramatic testament to how resurrected ocean floors directly dictate where life can flourish and where it must struggle to survive. Beyond just redirecting rainfall, these mountain ranges act as colossal barriers that physically reshape the planet's wind patterns. The Himalayas and the Tibetan Plateau, often called the Third Pole, are so immense that they effectively split the jet stream, those powerful high-altitude air currents that steer weather systems around the globe. During winter, this splitting helps create massive high-pressure systems over Siberia, influencing winter monsoon patterns across all of Asia. The mere presence of this uplifted seafloor, now standing over 5 miles high, alters atmospheric circulation on a hemispheric scale, demonstrating how a geological process can rewrite the rulebook for seasonal weather thousands of miles away from the mountains themselves. Perhaps the most significant climate connection lies in a subtle chemical process happening on the surface of these rocks. The very minerals that once formed on the deep seafloor, particularly silicate minerals like those in basalt and gabbro, are unusually reactive when exposed to Earth's atmosphere. When rainwater, which is slightly acidic due to dissolved carbon dioxide, falls on these freshly uplifted and fractured rocks, it triggers a chemical reaction called silicate weathering. This process slowly dissolves the rock, and in doing so, it pulls carbon dioxide out of the atmosphere, eventually transporting it via rivers to the ocean where it is stored in marine carbonate minerals for millions of years. This natural carbon sequestration is a fundamental part of the planet's long-term thermostat. The dramatic uplift of the Himalayas, for example, exposed vast quantities of fresh, reactive rock to monsoon rains, leading many scientists to propose that this accelerated weathering drew down so much atmospheric carbon dioxide that it contributed significantly to the global cooling that began around 50 million years ago and eventually led to the ice ages. It's a breathtaking concept that the collision of continents and the uplift of ancient seafloor could trigger a chemical chain reaction that ultimately changes the entire planet's climate, taking us from a warm, greenhouse world to the icehouse conditions we know today. The influence even extends beneath the waves, as the changing shape of the continents alters the very pathways of ocean currents. When the Central American Seaway closed due to the uplift of volcanic mountains and the formation of the Isthmus of Panama, it wasn't just a geographical event, it was an oceanographic revolution. This newly created land bridge, built from volcanic rocks and uplifted marine sediments, severed a major oceanic connection between the Atlantic and Pacific. It forced warm equatorial currents to change their course, ultimately helping to establish the Gulf Stream as we know it today. This powerful current began pumping vast amounts of warm water and heat toward the North Atlantic, moderating Europe's climate while simultaneously contributing to the conditions that allowed Arctic ice sheets to form. This single tectonic event, which involved the resurfacing of ocean floor as part of the Central American Arc, demonstrates how mountain building can rewrite the recipe for ocean circulation, with profound and lasting consequences for regional and global climate patterns that are still felt today. These intricate connections reveal a planet where the solid Earth, the oceans, the atmosphere, and the climate are not separate systems but deeply intertwined components of a single, dynamic whole. The process of ocean floor resurfacing is far more than a geological curiosity. It is a primary driver of environmental change, creating the diverse habitats and long-term climate stability that have allowed life to flourish and evolve. Every mountain range, therefore, stands as a monument to this incredible planetary partnership, where the slow dance of tectonics shapes not only the ground beneath our feet, but the very air we breathe and the climate we experience. Based on the relentless dance of tectonic plates we see today, we can actually forecast the next great acts in Earth's geological drama, predicting where the ocean floors of our time will eventually resurface as the magnificent mountain ranges of the distant future. This isn't speculation, it's a scientific projection based on measuring the current speeds and directions of continental drift, allowing us to extrapolate these motions millions of years forward. One of the most significant predictions involves the Atlantic Ocean, which might seem like a permanent feature of our world map but is, in geological terms, still a relatively young basin. Unlike the Pacific Ocean, which is ringed by subduction zones and is actively shrinking, the Atlantic has been widening since the breakup of Pangaea, with new crust constantly forming at the mid-Atlantic ridge. However, geologists believe this expansion won't continue forever. The immense weight of the Atlantic's own seafloor, as it ages, cools, and becomes denser, will eventually cause it to become gravitationally unstable. At that critical point, it will likely begin to sink, initiating new subduction zones along its margins. We might already be seeing the very earliest stages of this process off the coast of Portugal, where a region known as the Gibraltar Arc could represent a nascent subduction zone. If this continues, the ocean floor of the Atlantic will one day begin plunging beneath the eastern Americas and the western edges of Europe and Africa, setting the stage for a future collision that could weld the continents back together and uplift a new, colossal mountain range along these coasts, a potential future Pangaea with its own mighty Himalayas. A much more immediate and observable transformation is happening right now in the Mediterranean Sea. This iconic body of water is actually the last tiny remnant of the vast Tethys Ocean, which once separated the ancient supercontinents of Laurasia and Gondwana. The Mediterranean is essentially a collapsing ocean basin in its final death throes. The African plate continues to push northward, slowly but surely subducting the Mediterranean seafloor beneath southern Europe. This active subduction is the engine behind the intense volcanic activity of Mount Etna and Vesuvius in Italy, and the powerful earthquakes that regularly shake Greece and Turkey. The entire floor of this ancient sea is destined to be completely consumed, scrunched up, and accreted onto the southern edge of Europe, The result will be the continued growth and uplift of existing mountain chains like the Alps, the Apennines, and the Dinarides, as well as the probable creation of new peaks. Simultaneously, the northern edge of the African continent is being compressed and folded, building upon the Atlas Mountains in Morocco and Algeria. In a geological blink of an eye, the sunny beaches and holiday resorts of the Mediterranean coast will be replaced by the rugged, soaring peaks of a new mountain system, a permanent monument to the sea that once was. These long-range forecasts, spanning hundreds of millions of years, are crucial because they complete our perspective on Earth's dynamic nature. They transform our understanding from simply reading the past to actively anticipating the future evolution of our planet. By studying the full cycle from the birth of crust at mid-ocean ridges to its eventual destruction and resurrection in mountain belts, we gain a holistic view of plate tectonics as a continuous planetary-scale recycling system. This knowledge allows us to see the current configuration of our continents and oceans not as a permanent state, but as a single frame in a very long movie. While the timescales involved are so vast that they transcend any human concern, they hold a profound philosophical importance. They are a powerful reminder that the ground we perceive as solid and unchanging is part of a remarkably dynamic and active planet. The forces that built the ancient mountains we admire today are still at work, quietly and inexorably shaping the world of the far future, a world beyond our imagination but within our power to predict. Our ability to read the incredible story written in these rocks has been utterly transformed by a technological revolution, giving us powerful new eyes to see deep into both the Earth and deep time. Think of it this way: for generations, geologists were like detectives trying to solve a complex crime with only a magnifying glass and a notebook. Today, they have access to a full forensic laboratory, satellite surveillance, and supercomputers that can run simulations of the entire crime scene. It all starts high above our heads with eyes in the sky. High-resolution satellite imagery allows scientists to map massive, inaccessible mountain ranges from orbit, identifying rock types and major geological structures across entire continents with stunning clarity. But the real game changer in remote mapping is LiDAR, which stands for light detection and ranging. Imagine flying a plane over a dense forest and using lasers to digitally strip away every single tree and bush, revealing the bare rock beneath with centimeter-scale precision. This technology has uncovered previously invisible fault lines, landslide hazards, and subtle folds in the landscape, giving us a pristine, unedited view of the geological architecture that was once hidden by vegetation. The view doesn't stop at the surface. To understand how these pieces of ocean floor are assembled within a mountain belt, we need to see inside it, and that's where advanced geophysical techniques come in. Methods like seismic reflection work on a principle similar to an ultrasound for the planet. By creating powerful vibrations at the surface and meticulously measuring how the sound waves bounce off different rock layers deep underground, geophysicists can create detailed cross-sectional images of the Earth's crust, revealing how the ancient oceanic slabs are tilted, folded, and stacked. Other techniques, such as magnetotellurics, which measures the Earth's natural electrical and magnetic fields, can detect variations in how rocks conduct electricity, helping to identify different rock types and even the presence of fluids at incredible depths. These tools allow us to construct three-dimensional models of mountain ranges, visualizing the subterranean geometry that shows exactly how the ocean floor was emplaced. Once a promising rock is found in the field, its journey to reveal its secrets is just beginning. Back in the laboratory, it is subjected to a suite of analytical techniques that would have been pure science fiction a few decades ago. An electron microprobe allows scientists to focus a beam of electrons onto a single, tiny mineral grain within a rock-thin section, exciting its atoms and causing them to emit X-rays. By analyzing these X-rays, the probe can determine the exact chemical composition of that specific grain with astonishing accuracy, revealing the pressure and temperature conditions under which it formed. For an even deeper dive into a rock's origin story, we turn to mass spectrometry. This process can measure the ratios of different isotopes, slightly different forms of the same element, within a rock with incredible precision. These isotopic ratios act as a unique fingerprint, tracing the rock's source back to a specific type of mantle reservoir, or revealing the age of the minerals with unparalleled accuracy. It's this level of detail that allows a geologist to say with confidence that a particular rock in Switzerland originated from a mantle plume beneath a long-vanished ocean. All of this data doesn't just sit in isolation. It feeds into the digital realm of computational modeling. Modern supercomputers can now run sophisticated simulations that recreate the complex physics of subduction and mountain building over millions of years. Researchers can input variables like rock density, temperature, and plate convergence rates to test different scenarios, watching on screen as virtual continents collide and virtual ocean floors are subducted and uplifted. These models help us understand why some subducted crust is recycled into the mantle while other slices are exhumed back to the surface, solving some of the most enduring mysteries of the process. Perhaps the most daring technological endeavor is deep drilling. Projects like the Chinese Continental Scientific Drilling Program have drilled kilometers down into the heart of mountain ranges, retrieving pristine cores of rock from depths we could previously only infer. Holding a cylinder of rock that was once tens of kilometers underground is as close as we can get to time travel, providing direct, uncontested evidence of the conditions and processes at work deep within a collision zone. Together, this powerful suite of tools has transformed geology from a science of observation to one of profound insight, allowing us to not just describe these incredible transformations, but to truly understand the forces that drive them, revealing a dynamic planet whose secrets are gradually being unlocked through human ingenuity. Perhaps the most profound power of these resurrected ocean floors lies not just in what they tell scientists, but in their unparalleled ability to teach all of us. These magnificent mountain ranges, built from the foundations of vanished seas, serve as the world's greatest open-air classrooms, transforming complex abstract theories into something you can literally hold in your hand. The concept of plate tectonics can feel incredibly remote when confined to a textbook diagram, arrows on a page representing forces that move continents over millions of years. But when you stand at the foot of a towering cliff in the California coast ranges and place your palm on a chunk of serpentinite, a slick green rock that once was the Earth's mantle, those arrows suddenly become real. You are touching a piece of our planet's interior, a rock that should be dozens of kilometers underground, now brought to the surface by incomprehensible forces. That tangible connection ignites a deeper understanding that no lecture or animation can ever match. This is why geology field trips to these iconic locations are so much more than just scenic hikes. They are fundamental rites of passage for students. Walking through the Troodos ophiolite in Cyprus or scrambling over the Pillow basalts in Oman, a student isn't just learning about a sheeted dike complex. They are walking through one, seeing the countless vertical fractures that once channeled molten rock to the seafloor. They can trace the individual pillows in a lava flow, each blob-shaped structure telling a story of instant cooling against cold seawater. They can find chert layers packed with the microscopic skeletons of radiolarians, proving the immense depth and age of these rocks. This hands-on experience does more than teach facts. It builds a spatial and tactile intuition for geological processes. The immense scale of deep time, a concept that is notoriously difficult to grasp, suddenly clicks into place when you're holding a fossil from a creature that lived 200 million years ago in an ocean that no longer exists. The abstract idea of rock deformation becomes visceral when you struggle to climb over rock layers that have been bent and folded into impossible-looking curves by tectonic pressures. The educational value of these sites extends far beyond training the next generation of professional geologists. They are critical for cultivating a scientifically literate public, for helping everyone appreciate the dynamic planet we call home. When a visitor to a national park learns that the stunning peaks around them were once a tropical seafloor, it fundamentally shifts their perspective. It fosters a sense of deep time and planetary connection, replacing a static view of Earth with an appreciation for its ongoing, dynamic story. This understanding is the bedrock of informed environmental stewardship. How can we hope to understand and protect our planet if we don't first understand how it works on the most fundamental level? These landscapes teach the scientific method in action, showing how evidence is gathered, hypotheses are tested, and our understanding is continually refined. You see how geologists use the presence of a specific mineral, the orientation of a fault, or the sequence of rock layers to piece together a narrative from fragments of the past. Making these concepts accessible and engaging for a broad audience is one of geology's most important missions, and there's no better tool for this than the mountains themselves. Park rangers pointing out marine fossils on a high mountain trail, museum displays featuring polished slabs of gleaming eclogite, and interactive apps that let you overlay an ancient ocean onto a modern landscape. All of these efforts use the drama of resurfaced ocean floors to spark curiosity and wonder. This broader appreciation demystifies science, showing it not as a collection of settled facts but as an exciting, ongoing process of discovery. It helps people see the world around them with new eyes, to look at a familiar mountain range and perceive the epic journey of the rocks it contains, a journey from the fiery mantle to the abyssal plain and finally to the sunlit heights. This is the ultimate educational gift of these geological marvels. They don't just inform us about Earth's history, they inspire us to become lifelong students of its incredible story. This profound connection to deep time, revealed through the very stones beneath our feet, resonates far beyond the scientific community, touching the deepest parts of our human experience and cultural identity. For countless generations, long before the formal science of geology even existed, indigenous cultures around the world intuitively understood the sacredness and ancient wisdom embedded in the landscape. They didn't need mass spectrometers or satellite imagery to recognize that mountains were more than just piles of rock. They were living narratives, central characters in their creation stories and cosmologies. The Blackfeet Nation, for instance, speak of the chief mountain in Montana as the last remaining fragment of the backbone of the world, a primordial ridge from the beginning of time. In New Zealand, the Maori revere the mountain ranges of the North Island as the frozen body of their ancestor Maui, who pulled the land from the sea. These are not mere myths, they are sophisticated philosophical frameworks that embed human existence within a vast, animate, and storied planet, granting a sense of place and responsibility that modern society is only beginning to rediscover through our own scientific lens. This scientific revelation brings with it a powerful and necessary dose of humility for our contemporary world. In our daily lives, we operate on human time scales, we plan for decades, we record history in centuries, and we often speak of ancient ruins that are a few thousand years old with a sense of awe. But to stand before a mountain and understand that its core is a 200 million-year-old ocean floor completely recalibrates our sense of time and our place within it. Our entire recorded history, from the first written word to the latest space probe, is but a single, fleeting moment in the grand, multi-billion-year autobiography of Earth. This perspective doesn't diminish our achievements. Instead, it frames them within a far more majestic and awe-inspiring context. It challenges the anthropocentric view that we are the center of the universe and replaces it with a profound understanding that we are recent guests on a planet with its own long, complex, and independent history, a history that will continue to unfold long after we are gone. This shift in perspective is not just philosophical, it has urgent and practical implications for how we approach our role as stewards of this planet. When we look at environmental challenges like climate change or resource depletion, we often think in short-term political or economic cycles, but the deep time perspective forces us to consider the long-term consequences of our actions on a geological scale. It asks us to consider what kind of sedimentary layer humanity will leave in the rock record. Will it be a thin, strange band full of plastic particles and radioactive isotopes, a stark marker of a brief period of industrial explosion? Or will we learn to align our societies with the planet's long-term rhythms, creating a legacy of stability and integration, understanding that we are living on a dynamic, evolving planet, not a static stage, makes the concept of conservation not about preserving a museum piece, but about thoughtfully navigating our time within an ongoing, powerful geological story. It transforms environmentalism from a political stance into a simple act of intergenerational responsibility. Ultimately, this knowledge weaves a richer, more meaningful tapestry from the threads of science and spirit. It allows us to look at a sweeping mountain vista and see multiple dimensions simultaneously, the breathtaking beauty that stirs our soul, the incredible scientific story of subduction and uplift that engages our intellect, and the profound, humbling perspective of deep time that nourishes our spirit. These are not conflicting views but complementary ones, each deepening our appreciation of the others. The scientific understanding of how ocean floors become mountains doesn't erase the wonder, it magnifies it 1,000-fold. It gives us the tools to read the epic poem written in the landscape, to understand our own verse within it, and to contemplate the countless verses yet to be written. This is the true gift of this knowledge. It doesn't just tell us about the Earth's past. It helps us find our own place with both wisdom and humility within its immense and ongoing story. Even with all we've uncovered about this incredible planetary recycling system, some of the most fundamental questions remain tantalizingly unanswered, driving geologists to dig deeper, both literally and figuratively. One of the most perplexing mysteries is the journey of those ultra-high-pressure rocks, the ones that were dragged down to the very brink of the underworld. We know they made it back to the surface, but the how is a true geological head-scratcher. How did these rocks, which were subjected to pressures that should have turned them into molten blobs or simply assimilated them into the mantle, manage to stay intact and then travel dozens of kilometers back upward without being destroyed? It's like finding a perfectly preserved ice cube in a blast furnace. Current theories are like pieces of a complex puzzle. Some scientists propose that these rocks get trapped within a flow of less dense material that buoyantly rises back up, almost like being caught in a powerful updraft. Others suggest that changes in the angle or speed of the subducting slab can literally spit chunks of rock back out. There's even the idea of adduction, where a shift in tectonic forces causes the entire system to reverse course, pushing the deeply buried material back toward the surface. Each of these models has its merits, but none perfectly explains every occurrence, leaving the exhumation mechanism one of the field's most exciting and hotly debated topics. Closely tied to this is the selective preservation of some materials and the complete recycling of others. Not all ocean floor meets the same fate. Why do some vast sections of oceanic crust vanish without a trace into the mantle's depths, while other slivers, sometimes just a few kilometers wide, get meticulously preserved and uplifted for us to study? The answer seems to lie in the intricate dance of buoyancy and strength. Thicker, more buoyant features on the ocean floor, like massive underwater volcanoes called seamounts or oceanic plateaus, act like geological icebergs. They are too light and too stubborn to be pulled down easily. When they arrive at the subduction zone, they often resist subduction, getting bulldozed and scraped off onto the continent instead. The composition of the rock itself also plays a critical role. Wet, sedimentary layers are often weaker and get peeled off early in the process, forming accretionary prisms. Meanwhile, the stronger, drier basaltic heart of the oceanic crust might continue its descent, only to be regurgitated later under different conditions. It's a complex sorting mechanism that we are only beginning to understand, a geological filter that determines which parts of the ocean story are saved for the archives and which are permanently erased. Another major frontier of research involves the hidden role of fluids in this entire process. We often think of subduction as a colossal crunching of solid rock, but it's actually a very wet affair. The descending oceanic plate is like a giant water-logged sponge carrying water bound in minerals down into the depths. As pressure and heat increase, this water is squeezed out and it doesn't just sit there. These superheated fluids become incredibly potent agents of change. They dramatically lower the melting point of the surrounding mantle rock, triggering the volcanic activity that lines the continents. But they also facilitate chemical reactions, transforming rock compositions and potentially creating pathways of weakness that allow deeply buried rocks to detach and begin their journey back up. The precise pathways these fluids take, how much they transport, and their exact influence on rock strength and melting are subjects of intense study, with researchers using sophisticated computer models and high-pressure laboratory experiments to simulate these extreme conditions. Even the basic mechanics of mountain building itself hold surprises. The relationship between how fast plates converge and how high a mountain range becomes is not a simple one-to-one correlation. Why do some slow-moving collisions, like the one in Taiwan, create incredibly steep and dramatic topography so quickly, while other faster collisions have more muted effects? The answer likely involves the complex interplay between the strength of the converging plates, the angle of subduction, and the efficiency of erosion. Erosion itself is now understood to be far more than just a passive bystander shaving off the top. It's an active player in the tectonic system. The rapid removal of material by rivers and glaciers can actually pull deeper rocks upward through isostatic rebound, effectively controlling the rate at which the deep geological record is exposed. This feedback loop between climate-driven erosion and tectonic uplift is a vibrant new area of interdisciplinary research, merging geology with climatology. These persistent questions are not signs of failure but are the very lifeblood of science, guaranteeing that the study of our dynamic planet will remain a thrilling adventure of discovery for generations to come. Every new satellite, every more powerful computer model, and every drill core pulled from a deep fault zone brings us closer to answers, while almost certainly revealing new and even more fascinating mysteries about how the Earth tirelessly recycles its own surface, writing its history in the stones of the highest peak.